Enlightened science, chemistry catches up. Historians often refer to a period more or less following the Renaissance as the Enlightenment, a name also given to the philosophical movement that reaches its peak in the second half of the 18th century. The basic feature of Enlightenment was a belief in the superiority of reason over superstition. This incorporated the idea that humankind was in the process of progressing socially so that the future would be an improvement in the past. And one of those improvements was a challenge to Orthodox religion with its overtones of superstition. Both the American and French Revolution were justified intellectually, in part on the basis of human rights, a guiding principle of Enlightenment philosophers such as Voltaire and activists such as Thomas Paine. Although it was just one of the many factors in the Enlightenment, the success of Newtonian physics is providing a mathematical description of an ordered world clearly played a big part in the flowering of this movement in the 18th century, encouraging philosophers of a rationalist persuasion and also encouraging chemists and biologists to think that their parts of the natural world might be explained on the basis of simple laws. It isn't so much that Linnaeus, say, consciously modeled his approach on Newton, but rather the idea of order and rationality as a way of to investigate the world had taken root by the early 18th century and seemed the obvious way forward. It is probably not entirely a coincidence that the Industrial Revolution took place first in England in round terms during the period from 1740 to 1780 before spreading to the rest of Europe. There are many factors which contributed to this revolution occurring when and where it did, including the geographical and geological circumstances of Britain, or an island of coal, that the early flowering of what might be called democracy. While France was still ruled by the conservative and aristocratic ancient regime, and Germany was a fragmented cluster of statelets, perhaps an element of pure chance. But one of the factors was that the Newtonian mechanistic world view became firmly established most quickly, naturally enough, in Newton's homeland. Once the Industrial Revolution got underway, it gave a huge boost to science, both by stimulating interest in topics such as heat and thermodynamics, of great practice and commercial importance in the steam age, and in providing new tools for scientists to use in their investigations of the world. Nowhere is this seen more clearly than the case of use of chemistry. It isn't because chemists were particularly stupid or superstitious that they lagged behind the other sciences, particularly physics, until well into the 18th century. They simply lacked the tools for the job. Astronomy could be carried out to some extent without any tools at all, using only the human eye. Physics in the 17th century involves studying easily manipulated objects such as balls rolling down inclined planes or the swing of the pendulum. Even botanists and zoologists could make progress with the aid of simplest magnifying glasses and microscopes. But what chemists needed, above all, was a reliable and controllable source of heat to encourage chemical reactions. If your source of heat was basically a blacksmith's forge and you couldn't measure temperatures, any chemical experimenting was bound to be a bit rough and ready. Even in the 19th century, to provide more controllable heat and make more subtle experiments, chemists were forced to use different numbers of candles or split lamps with several different wicks that could be lit or extinguished individually. To obtain a localized source of intense heat, they had to use a burning glass to concentrate the rays of the sun. As for making accurate measurements of what was going on, Gabriel Fahrenheit 1686 to 1736 invented the alcohol thermometer only in 1709 and did not come up with the mercury thermometer until 1714, when he also developed the temperature scale now named in his honor. Castes in India, B.R. Ambedkar. The problem of castes then ultimately resolves itself into one of repairing the disparity between the manageable units of the two sexes within it. Left to nature, the much needed parity between the units can be realized only when a couple dies simultaneously, but this is a rare contingency. The husband may die before the wife and create a surplus woman who must be disposed of, else through remarriage or she will create a else through intermarriage she will violate the endogamy of the group. In like manner, the husband may survive his wife and be surplus man whom the group, while it may sympathize with him for the sad bereavement, has to dispose of, else he will marry outside the caste and will break the endogamy. Thus, both the surplus man and the surplus woman constitute a menace to the caste if not taken care of. For not finding suitable partners inside their preached circle and left to themselves, they cannot find any, for if the latter be not regulated, there can only be just enough pairs to go round. Very likely they will transgress the boundary, marry outside, and import offspring that is foreign to the caste. Let us see what our imaginary group is likely to do with this surplus man and surplus woman. We will first take up the case of the surplus woman. She can be disposed of in two different ways so as to preserve the endogamy of the caste. First, burn her on the funeral pyre of her deceased husband and get rid of her. This, however, is rather an impracticable way of solving the problem of sex disparity. In some cases, it may work, in others, it may not. Consequently, every surplus woman cannot thus be disposed of because it is an easy solution but a hard realization. So the surplus woman, widow, if not disposed of, remains in the group, but in her very existence lies a double danger. She may marry outside the caste and violate endogamy, or she may marry within the caste and through competition encroach upon the chances of marriage that must be reserved for the potential brides in the caste. She is therefore a menace in any case, and something must be done to her if she cannot be burned along with her deceased husband. The second remedy is to enforce widowhood on her for the rest of her life. So far as the objective results are concerned, burning is a better solution than enforcing widowhood. Burning the widow eliminates all the evils that a surplus woman is fraught with. Being dead and gone, she creates no problem of remarriage, either inside or outside the caste, but compulsory widowhood is superior to burning because it is more practicable. Besides being comparatively humane, it also guards against the evils of remarriage, as does burning, but it fails to guard the morals of the group. No doubt, under compulsory widowhood, the woman remains, and just because she is deprived of her natural right of being a legitimate wife in future, the incentive to immoral conduct is decreased. But this is by no means an insuperable difficulty. She can be degraded to a condition in which she is no longer a source of allurement. The problem of surplus man widower is much more important and much more difficult than that of the surplus woman to a group that desires to make itself into the caste. From time immemorial, man, as compared with women, has had the upper hand. He is a dominant figure in every group and of the two sexes has greater prestige. With this traditional superiority of man over woman, his wishes have always been consulted. On the woman, on the other hand, has been an easy prey to all kinds of iniquitous injunctions, religious, social, or economic. But as man as a maker of injunctions is most often above them all. Such being the case, you cannot accord the same kind of treatment to a surplus man as you can to a surplus woman in a caste. From fish to infinity. The best introduction of number to numbers I have ever seen, the clearest and funniest explanation of what they are and why we need them, appears in Sesame Street video called 123 Count With Me. Humphrey, an amiable but dim-witted fellow with a pink fur and a green nose, is working the lunch shift at the Fuddy Adams Hotel when he takes a call from a room full of penguins. Humphrey listens carefully and then calls out their order to the kitchen. Fish, 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 fish. This prompts Ernie to enlighten him about the virtues of the number 6. Children learn from this that numbers are wonderful shortcuts. Instead of saying the word fish exactly as many times as they are penguins, Humphrey could use the more powerful concepts of 6. As adults, however, we might notice a potential downside to numbers. Surely they are great time savers, but at a serious cost in abstraction. 6 is more ethereal than 6 fish. Precisely because it is more general. It applies to 6 of anything: 6 plates, 6 penguins, 6 utterances of the word fish. It is the ineffable thing they all have in common. Viewed in this light, numbers start to seem a bit mysterious. They apparently exist in some sort of Platonic realm, a level above reality. In that respect, they are more like the other lofty concepts, truth and justice, less like ordinary objects of daily life. Their philosophical status becomes more murkier upon for further reflection. Where exactly do numbers come from? Did humanity invent them or discover them? An additional subtlety is that numbers and all mathematical ideas from that matter have lives of their own. We can't control them, even though they exist in our minds. Once we decide what we mean by them, we have no say in how they believe. They obey certain laws and have certain properties, personalities, and a way of combining with one another, and there is nothing we can do about it except watch and try to understand. In that sense, they are eerily reminiscent of atoms and stars, the things of this world, which are likewise subject to laws beyond our control, except that those things exist outside of our heads. This dual aspect of numbers, as part heaven, part earth, is perhaps the most paradoxical feature, and the feature that makes them so useful. It is what the physicist Eugen Wigner had in mind when he wrote of the unreasonable effectiveness of mathematics in the natural sciences. In case it's not clear what I mean about the lives of numbers and their uncontrollable behavior, let's go back to the furry Adams. Suppose that before Humphrey puts in the penguin's order, he suddenly gets a call on another line from a room occupied by the same number of penguins, all of them also clamoring for fish. After taking both calls, what should Humphrey yell out to the kitchen? If he hasn't learned anything, he could shout fish once for each penguin, or using his numbers, he could tell the cook he needs 6 orders of fish for the first room and 6 more for the second room. But what he really needs is a new concept, addition. Once he mastered it, he'll proudly say he needs 6 plus 6, or if he is a show off, 12 fish. This creative process here is the same as the one that gave us numbers in the first place. Just as numbers are a shortcut for counting by ones, addition is a shortcut for counting by any amount. This is how mathematics grows. The right of abstraction leads to new insight and new power. Before long, even Humphrey might realize he can keep counting for forever. Yet, despite this infinite in the vista, there are always constraints on our creativity. We can decide what we mean by things like 6 and plus, but once we do, the results of expressions like 6 plus 6 are beyond our control. Logic leaves us no choice. In that sense, math always involves both invention and discovery. We invent the concepts but discover their consequences.